So just to jog our memory, here was the problem that we had to address. We said, okay, if we have cosmic orbital potential energy, we can't use MGH because G changes. I told you we could tackle it by looking at the area under a force versus separation distance graph. The problem is we don't know how to find the area under a curve. And so I had to do a little bit of hand waving, but we ended up with this equation here. We made it negative because force is the derivative of potential energy, if you're in calculus. We made it negative because we defined 0 relative to infinity. And then we could still use all of our energy stuff. Work is still change in potential plus change in kinetic. The law of conservation of energy is still kinetic initial plus potential initial equals kinetic final plus potential final. It's just much more awkward because potential energy is not 0 on the Earth. Where's the only place potential energy will be 0? Out at infinity, which we are going to look at something like that, by the way. And in real life, instead of out at infinity, if you want the real life, when you're a few million miles away from, or kilometers away from the Earth, then gravity is small enough that, it's negligible. Okay? But we started doing all the same stuff. We said, you know what? We can drop an object and figure out how fast it hits the ground. It's just we have to go cosmic. We can lift something up. It's just we have to go cosmic. We can put something in orbit, which means lifting it up and giving it kinetic energy. Example 3. Suppose we launch a missile from the Earth, and we use all of its fuel in one initial burst. So we're going to fire the rocket and then shut off the rocket and let it coast the rest of the way. It's a thought experiment, and we're going to ignore air resistance because that makes the math yucky. So the only force that it experiences as it rises is gravity. As it rises, what happens to the kinetic energy and the potential energy? Let's do kinetic first. I've taught you never read these across ever. Always read these up and down. So, by the way, this is the same physics as tossing something in the air. We're just going cosmic. So as I toss an object in the air, as it rises, what happens to its speed? So what happens to its kinetic energy? So we're going to go no, no, yes, yes. As it rises, what happens to its potential energy? It increases. Why? Because that kinetic energy has to go somewhere. And even in our cosmic one, even with that negative, that don't freak out about it, you are gaining potential energy because you're so far negative that you need to gain enough energy to reach 0. You have to gain energy. So increases, doesn't decrease. Increase, doesn't decrease. What's the correct answer? For some reason, I left a whole bunch of room on this page. I don't know why, but you know why? Because we need a whole bunch of room for this next question. That's why. I like example 4, I like example 4. Example 4 is a nice question. And what I mean by that is I am going to ask you how much work required to put something in orbit, which is what B is asking me to find. Are we in orbit? Is the orbit stable?
Yep.
Okay. So do we have kinetic energy then? We must. In fact, you know what I would do, folks? I would underline stable orbit because the word orbit is also a bit of a trigger phrase for me in this unit. Kind of what goes through my mind, except with words. Well, what's the first thing they want me to find?
The radius. Orbital.
What radius?
Orbital.
What radius?
Orbital.
Gravity is what's pulling me. Did you say orbit? Right. That's. It's not a no-brainer, but that's going to be my first approach. Are we going into outer space? So I can't use little m, little g for gravity. So it's going to be big G, big M, little m over r squared equals m. Which version of A am I going to use here? How do you know? Oh, they gave me a V? Okay. Some stuff cancels in this version. Little m, one of the r's, What am I trying to find?
Speed.
What am I trying to find?
Oh, the radius, sorry.
Where is the R right now? On the...
Bottom.
Ugh. Oh, wait a minute. I think I can times it over. Yes? And then what will I do with that V squared that was on that side? Divide it. Do I need to square root the R or anything? Is there a squared on the R anymore? Okay, a common mistake, because there was a squared on the R, but it canceled. Kids square root, or they're just so used to square rooting for a lot of these. So if I hear you correctly, Wild, I think I do, you're telling me yet another equation. R apparently is big G, big M over V squared? Okay. And that's, yeah, I can figure out the orbital radius. Oh, by the way, somebody asked me during the flex, Mr. Duick, would you ever ask us to find big M? Sure. If you knew the speed and the radius, you could find the mass of the, starting from here, you could find the mass of the planet. Believe it or not, that's how we figure out the mass of exoplanets and stars. We observe, we can figure out their period very easily by observation and their radius, and we can then figure out missing masses. Sure. Meanwhile, big G is 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 4,200 squared. .67 times 10 to the negative 11 times 5.98 times 10 to the 24th divided by 4,200 squared. Do you get 2, 2, 6, 1, that there? Yeah.
If there's a satellite, are we always saying it's the big M is Earth then? It's not going to be on a planet?
Unless I decided that we were going to orbit the moon, because the moon is technically classified as a satellite. But what's causing the gravity is big M. So that celestial object which is sending out its gravitational field, that's the big M.
But you just said just a satellite with no big M, so do we just assume it's Earth then? You just say it's a satellite?
Oh, here?
Yeah.
If I don't mention a planet, assume it's Earth. In other words, if we're going to the moon, or I may have told you yesterday, and if not, I'm going to tell you now. On the test, we're going to go near a black hole just for giggles, because how can I not? And I'll make it obvious. Don't use M, Earth here. Either I'll give you a mass of a planet, if it's a mystery planet. I think on my final exam one year, I did Planet Duick, which had a mass of pi times 10 to the 8th or something like that, and a radius of E times 10 to the 6th, because that's the planet I would design if I was in charge. Anyway, yeah, it'll be obvious. But so big M is going to be the mass of the planet that's causing the gravitational field, and if I don't give you a specific one, assume it's Earth. Do you get that there? So 2.26 times 10 to the 1, 2, 3, 4, 5, 6, 7? Now, I'm going to write that, but you know I'm going to store this on my calculator because I bet you I'm going to need this. Tato, what's B want me to find?
Work.
Oh, that's easy. I can just go work equals force times distance, right? Or can I? What force are we doing work against? If we're putting something... is gravity a constant force as I move away from the Earth?
No.
So what's our other definition of work from our formula sheet that you have in front of you, or that you could...
Change the potential.
Now, if this question didn't say orbit, if it just asked how much work to lift, I could cross out the change in kinetic. But are we in a stable orbit?
Yeah.
So do we have to have also kinetic energy?
Yep.
Yeah. By the way, you may have noticed, Sarah, we're getting really big answers when we calculate how much work. Yesterday I was watching a TED Talk by an astronaut. On most rockets, 95% of the mass is fuel, only 5% of the mass is payload. Yeah. It's rocket science. And so as much as I would love it, Sharon, if in your lifetime space tourism became a thing, unless we come up with some magic Star Trek warp drive technology, which would be great, it's just so prohibitively cost expensive because you can't beat the law of energy. It's a law. What do you want to find first? Potential, change in potential, or change in kinetic? Doesn't matter.
We'll go potential.
Change in potential? Okay. What's changing anything? Can I use MGH initial final minus MGH initial? We're cosmic? Okay. Good yawn, Jaden?
Oh, yeah.
Now, our final, by the way, I think that's going to be our orbit. That's where we're ending up. In fact, that's going to be our answer from part A. Our initial, we'll assume we're starting out from the surface of the Earth. Okay. Lots of writing here. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. I've scrolled down. How heavy was the satellite? What was the mass of the satellite? 1800. Thank you. Divided by, now I'm going to write 2.26 times 10 to the 7th, but what am I actually going to use on my calculator? My answer button. What's a minus minus the same as? That's, by the way, what's going to give us a positive answer, because it should take positive work to do this. So as long as you're careful with the signs, they'll take care of themselves. And then what I said to you yesterday, Tato, is just go ditto mark times ditto mark times ditto mark. And all that's going to be there is the 6.38 times 10 to the 6th. Less writing, less chance of making a dumb mistake, and less typing. And we're going to go one fraction at a time. You know what I just noticed? The last calculation that we did, I have a 6.67 and a 5.98. I'm just going to backspace, and all I need to do is put my... I need to multiply by 1800 and then divide by answer button. Why not use that? And I get my final potential energy. Oh, I forgot the negative. Oh, I can fix that in my head easily by just putting a negative in front. Do you get negative 3.1752 times 10 to the 10th? And this was nice. It works out evenly, which doesn't happen very often, but I'll take that. 3.1752 times 10 to the negative. Oh. What did I say it was? 1752 times 10 to the 10th plus. And now I repeat, but instead of answer button, I have 6.38 times 10 to the 6th. That one didn't work out evenly. 1.1253. If I go to 5 sig figs in my data, that usually IRA gives me 3 sig figs of accuracy in my final answer, and that's all I'm fussy about. And I think I mentioned, but I'll say it again, those of you that have these constants built into your calculator, and some of you do, if, for example, if you're using big G, I'm writing 6.67 times 10 to the negative 11. I think yours is accurate to 5 or 6 sig figs, and so you're going to find by the 3rd or 4th decimal, you don't match me anymore. It's okay. As long as we're close, yes? 1.1253 times 10 to the 11th. And I'm going to add these two numbers. Well, I got this one stored, so I'm just going to go take away 3.1752. 752, Mr. Dewick. Why did you write 25? That was silly. 52 times 10 to the 10th. Do you get a positive answer, a change in potential of 8.078 times 10 to the 10th? Put a box around it, and we'll come back to it. Tato, that's the change in potential. What else do we need to find? The change in? What's change in anything? It's going to be a half mv final squared minus a half mv initial squared. But what did we say yesterday? What's our initial kinetic energy going to be? Unless the question specifically says different and gives us an initial speed, what are we going to assume our initial speed is? 0. Is it really? No, I said as long as we pretend we're working for Superman. We're always going to be launching from the Fortress of Solitude at the North Pole, which none of my Block H class knew. Huh. I don't know where Superman... Oh, boy. Next to Santa Claus, and they're both real. So it's going to be 0.5. What was M? 1800? Did they give me V? Now, if they hadn't, they could have given me R, orbital radius, and then I would have gone, gravity is what's pulling me in a circle. And I could have found it. What was it, 4200? That's a little nicer. Squared. And I get 1.586 times 10 to the 10th. Is that right? 1.5876. Sorry, I don't think I said the 7. 1.5876. That's the change in kinetic. Tata, what am I going to do with the change in potential and the change in kinetic? So it's going to be 8.078 times 10 to the 10th. That's to 4 sig figs plus 1.5876 times 10 to the 10th. That's to 5 sig figs. I should be good to 3 sig figs with this data. I don't need to retype the second one. So I'm just going to add 8.078 times 10 to the 10th. Do you get 9.665? You know what? 9.67. I would take 9.66 or 9.68. There's enough variance depending on which calculator you're using. But 9.6 something. 9.67 times 10 to the 10th. Is that okay? So what's your homework? Here's what I assigned my other class. Can you circle 1, 2, 3? You can skip 4, 5, 6. You want to do number 7? Number 7, we're dropping an object from outer space. A is asking you to find the initial potential energy. B is asking you to find the final potential energy. C is asking you to find the speed. Honestly, on a test, I think I would just say, find the speed. Because you can actually do that all in one step. But you can do it in chunks, too. Skip 8. 9 is good. $11 is good. 13 is cool. We skipped 12. We skipped 10. 14 is good. 15 is good. What's 14 asking you to find? Impact speed. This is an asteroid collision. Well, in this case, it's a space probe. But asteroids can hit the Earth at pretty big speeds, and they can do a lot of damage. Massive damage. Like the asteroid that's going to hit the Earth in 2034.